For simple single voltage source circuits, there are two ways that loads can be set up in the circuit. One is what we say is when resistors or loads are in series. That's what we see in this first diagram, where the resistors are in line with one another, so there's just a single loop in the circuit. And then we can have what's called a parallel set of resistors. So we can have two or more parallel tracks through which the current is going to flow. Now, because of conservation in charge, whatever is exiting the battery has to be the same current that re-enters it. So in the case of a series circuit, you're going to have the exact same current at every single point of the circuit. So what exits the battery is the same as the current that's traveling through the first resistor, which is the same as the current that's traveling through the second resistor, regardless of whether those resistances are the same or if they're different. In the case of the parallel circuit, the same thing applies. Whatever exits the battery has to be the same as what re-enters it. But when we split into the two parallel resistors that we see here, or more if we had an extra loop or two, the sums of these two currents is going to equal what exited the battery and what re-enters. So we can have different currents that are flowing through those resistors, and that's going to happen if those resistors have different resistances. But in total, the sum of those has to be the same as what exited the battery and what enters the battery. Now in these two scenarios, the resistance is not just calculated by adding the resistors that we see, because obviously the pathways are different, so we have to treat those differently. So that's what we'll explore next. So in our first example, we have a series circuit. So we have a 12-volt battery, and then we have two 100-ohm resistors. And so we want to know what is the current in the circuit and what is the voltage drop across each of these resistors. So if you recall from our first notes, whatever the potential is here is going to be the same until we reach this first resistor. Then we're going to have some sort of drop across this resistor. Then we're going to have another drop across the second resistor. But when we get down to here, we're going to end up with a full drop of 12 volts. So if the battery is providing a 12-volt step up in voltage across its terminals, so here we have a potential of 12 volts, and then here we have a potential of 0 volts. And so we have a combined drop that's going to happen across those two resistors. It may be easier if we draw the circuit like this. So same circuit, same two resistors, same single loop, but now here's our 12 volt, here's our 0 volt potential. So that means the sum of the voltage drops across those two resistors has to equal 12. And so from Ohm's law, we know that V equals I times R, so voltage equals current times resistance. So in our case here, for the battery, it's going to equal the current times resistor 1 plus the current times resistor 2, since those are in line with each other, and as we showed here, the sums of those two voltage drops has to equal the 12 volts that is being supplied by the battery. So that current is the same in both of these because it's a single loop. If these were in parallel, then we would have to treat those currents differently. So to solve then, we can say that we've got our 12 volts here equals I times, and each of these resistors is 100 ohms, so I times 100 plus another I times 100. So we're looking at 12 volts equals 200 I. And so then if we divide both sides by 200 and then round to our three significant figures, I'm sorry, we've got 0.600 amps as our result. And so to figure out the voltage drop across each one of these, we're just going to plug that into each of these individual I times R1 and I times R2, but because those two are the same, we're going to end up with a voltage drop of 6 volts across each of those resistors. And so down below here we can see that if we want to figure out what the equivalent resistance across for a series circuit is, then all we have to do is just add the resistors that are in series with each other. So if we have two resistors in line, then we just add those, 100 plus 100, we have a combined equivalent resistance of 200 ohms. If we had three resistors or four or five that are all in line with each other, in series with each other, then we just keep on adding all of those resistances. So the more loads we apply to the circuit, the greater the resistance, and so therefore the amount of current that's going to be passing through that circuit is going to drop as you increase the resistance, since we have an inverse relationship here. So the voltage is staying constant, but the current is going to drop as the resistance goes up. Likewise, if the resistance goes down, the current's going to go up. Now in this parallel circuit, we have the same components. So we still have a 12-volt battery. We've got two 100 ohm resistors. But now those resistors are in parallel with one another instead of being in series. So how does that change things? Well, again, remember that the potential at any point along this circuit before we hit a load is going to be that full 12 volts. So that means we're at 12 volts of potential all throughout this part of the circuit. And then once we pass through those resistors, now everywhere along this bottom part of the circuit, we have a potential of 0 volts. So that means that the voltage drop across each of those 100 ohm resistors is going to be 12 volts. It's going to be the equivalent of what is being provided by the battery. Or in other words, the voltage across the battery is going to be equal to I times R1, if we call this one R1 and this one R2, and that's going to be equal to I times R2. So those voltage drops across those are the same because the voltage potential at the top of the circuit is 12 volts. The voltage potential at the bottom of the circuit is 0 volts, and so that's the same across both of those resistors. So, and we should probably label these as I1 and I2 here, since those could be different. They're going to be the same in this case because we have the exact same two resistors, but they would be different if those resistance values were different. So what this means is we've got this 12 volts equals, so then we've got I1 times our 100 ohm resistor, and then that's also equal to I2 times that 100 ohm resistor. So if we divide everything by 100, we'll get that I1 is equal to I2, which is equal to 0.12 amps. So those are the currents that are traveling through each of those resistors. But that's not the current that's being drawn from the battery. The current that's being drawn from the battery is the sum of those. Because again, we have current I1 traveling through the first battery. We have current I2 that's traveling through, or resistor, sorry, I2 that's traveling through the second. And so those together, by conservation of charge, have to add up to the total current. So I, the current that's being drawn from the battery, is equal to I1 plus I2. So taken together, 0.12 plus 0.12, we get 0.24, and then we should keep our significant figures here. 0 amps is the total current that's being drawn from the circuit. So if we compare that to the previous problem where the current that was being drawn from the battery was just 0.6 amps, we can see that with the same three components, a battery of 12 volts and then two resistors of 100 ohms each, we have significantly different amount of current that's being drawn from the battery in these two configurations. And so what this tells us is, since we have this inverse relationship, putting these resistors in parallel with each other has increased the current, which means it has decreased the resistance in the circuit, whereas putting them in parallel increases the resistance. So that's the difference between the two. Parallel resistances end up providing more pathways for the current to be able to make its way through the circuit. So therefore that reduces the resistance in the circuit. But putting those same resistors in series with each other increases the resistance. So we can piece together a way of calculating what the equivalent resistance is for a parallel set of resistors as follows. So if you recall, for a series circuit, you just add up those resistances. Well, in the case of a parallel circuit, we saw that the current that's being drawn from the battery, I, is going to be equal to the sums of the currents that are going through each of the parallel resistors. So in our case, we had the two parallel resistors. We just had I1 plus I2 added up to make the total current being drawn from the battery. If we had more resistors, more parallel resistors, then we would have more currents that we would add together. So that's what we have here in this first statement. So again, we also said that the voltage drop across all of those resistors is the same, since the potential across the top of the circuit, if we have all these parallel resistors, the voltage potential across the top is the same for all the resistors. The voltage potential at the bottom is the same for all those resistors. So the voltage drop across all of them is the same as what it is for the battery. So what we can say is we've got the voltage, which is V uniform throughout for the circuit. So we can say that the voltage divided by the equivalent resistance of all of those resistors is equal to I. So just rearranging Ohm's law, V equals I times R. To solve for I, we'd have V over R. So the voltage divided by the equivalent resistance is going to be equal to the voltage divided by the first resistor plus the voltage divided by the second, the third, and so on. And so then, since V is uniform throughout, if we divide everything by V, that just wipes out all the V's that are in the numerator. And so then we end up with an equation that we can use to calculate for the equivalent resistance of a set of parallel resistors, where the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the resistors. So we can use this as a means for eventually calculating the equivalent resistance. So for our example before, 1 over R EQ would be 1 over 100 plus 1 over 100, since both of those resistors had resistances of 100 ohms. So that would mean I'd have 1 over R EQ equals 2 over 100, or 1/50th. So we want to make sure that we don't make the mistake of saying that our equivalent resistance is 1/50th. That's the reciprocal of the equivalent resistance. So in that circuit there, our equivalent resistance was 50 ohms. And if you'll recall from the previous example, the series circuit, where the two were in series, we would have had an equivalent resistance of 200 ohms. So here we end up with a much lower resistance by putting those same two resistors in parallel as we do when we put them in series.